Let us see now what are the major process safeguards applied in the turbines and engines. So gas turbines and gas diesel engine needs the following process and mechanical safeguarding as a minimum. It needs overpressure protection, overspeed protection, over temperature and loss of flame on gas turbines, protection against loss of lube oil, enclosure to detect fire and gas, loss of seal gas, high level of vibration. These are the minimum safeguards which are normally applied for gas turbines or gas diesel engines. For heat exchangers, if reasonably practical, the hydrotest pressure of the low pressure side of the shell and tube heat exchangers should be greater than the design pressure of the high pressure side. So low pressure side hydrotest pressure should be at least equal or greater than the design pressure of the high pressure side. If that is practical in terms of the economy, then we can do such a kind of design. So this will avoid some of the major relieving scenarios which you will study during the safeguarding system application for the heat exchanger. But in case if it is not practical or if it is not economical, then you have to design your release system for certain release scenario which are very critical and which are really very complex in terms of identification of total relieving load. So where this condition cannot be met, a relief device should be installed in size for the flow corresponding to burst of a single tube for shell and tube heat exchanger, or if it is a printed circuit heat exchanger, then rupture of the running longitudinal to a corrugation for a printed circuit heat exchanger has to be considered, or the failure of the single plate in a plate heat exchanger has to be considered. So based on what type of heat exchanger it is, accordingly you have to consider the failure of the one of the weak component, and then you have to find out the relieving load on the for the system of the heat exchanger. So you will find the definitive criteria with respect to identification of the scenario from your company's company specific safeguarding philosophies. But in general, if you go towards to API references, you will find the reference of the low pressure and high pressure sides, hydrotest pressure and design pressure that needs to be compared, and then accordingly you have to reach to the conclusion that whether you have to apply the burst of a tube as one of the scenario of relieving. Let us see the fired heater. What are the major safeguards? The key process safeguards for fire heaters are flame detector trip, low fuel pressure trip, low airflow trip, forced draft fan motor trip, low air fuel ratio trip, high fuel pressure trip, and high level fuel gas knockout drum. So these are some of the safeguards for the fired heater. Piping system. Piping systems are protected against overpressure by upstream or downstream equipment. In case a section of a piping is blocked in, overpressure might occur due to thermal expansion. So let's say there is a part of a piping which has been blocked on the upstream and downstream side, both sides, and there is a block liquid or a block fluid within that between those two valves. And such a section, if it is subjected to thermal radiation, what will happen is it will expand eventually, and that will require a thermal release. So this is provided by a thermal relief valve. So on the cold side of a heat exchanger, which can be blocked in as the heat rises, may be rapid and result in a relief rate greater than that which may be passed by valves. So cold side of a heat exchanger which can be blocked in, and then you have to then in such situations you have to provide a relief valve. Section of piping containing more than 500 liter or substantially flashing liquid as a release through flanges or rupture would pose a significant fire risk. So if there is a piping section having more than 500 liter of such flashing liquids, you have to provide the relief valve, thermal relief valve. piping in storage areas or transport lines which will be regularly blocked in during the normal operation. So they have given a general guideline like 3 times a year or more. So such a such a piping network are very frequent. You'll have to frequently rely on the wall leakage. So in such cases, you have to provide a thermal relief valve. So these are some of the guidelines under which you have to consider a thermal relief protection for the piping system. Let us see now the pipeline. Pipelines can be fully rated or protected against overpressure by relief valves, IPF or high integrity protection system. So if there is a pipeline which is getting the feed from the upstream pump, and if your pump can generate, let's say in general it is operating at normal operating pressure of 50 bar, whereas your pump can can cause a shut-in pressure of up to, let's say, 75 bar. So you can design your downstream pipeline to up to 75 bar. So actually your pipeline can take full pressure. So in such a situation, you will call that pipeline is fully rated for the upstream equipment design condition. But sometimes you may not be able to justify such cost of a 75 bar design pressure pipeline, and you may go for a smaller design pressure, let's say 60 bar as a design pressure, whereas normal operating pressure is a 50 bar. Then you will have to provide a relief valve which is set at a 60 bar, and it will not allow the pressure of the system to go more than the design pressure of the pipeline. So all we are going to are again those three options. Either you can provide a fully rated system, or you can provide a relief valve, or the third option, which is IPF or a HIPS protection. The most common protection method is by relief valve normally in pipelines. Let us see now the plant blowdown. The objective of the plant blowdown system is to prevent major escalation during a fire or explosion incident. The relief valve does not provide the same level of protection during a fire, since the pressure in the vessel would remain the same as the temperature increase and the vessel strength is reduced. So plant blowdown would therefore be required. So one of the API, which is API 521, which is normally referred standard on pressure relieving and depressuring system, provides rules for such a blowdown. Some of the important points to be considered for blowdown designs are listed below. So essentially it calls for a reduction of a pressure to less than 50% of the design pressure within 15 minutes, which should be considered as the minimum of requirement. So let's say your equipment is designed for 100 bar, and there is a plant ESD situation has come. An operator has pressed a button for ESD of the system. So what will happen is, if there is a 100 bar design pressure equipment, the blowdown valve of that particular equipment will open. So what is expected out of that blowdown valve is it should depressurize the equipment's pressure from 100 bar to 50 bar within a 15 minutes time frame at least. So that doesn't mean that the depressuring will stop after 15 minutes. It will still continue depressuring the equipment. But as a minimum, it should at least reduce to 50% of the design pressure within 15 minutes of time frame. Now this particular guideline is given by API, but there may be company specific guidelines wherein they may ask you to design the equipment depressuring system to reduce to 50% of design pressure, or some other specified value, let's say 7 bar as the pressure, whichever is lower. So your equipment should reach at least to that level in the 15 minutes of time. So accordingly we have to design the blowdown system. So if the downstream blowdown valve has to be accordingly sized for depressuring the equipment within that specified 15 minutes time frame. And in general, minor inventories like less than 50 kg can be neglected due to their limited escalation potential. So this is the typical guideline used for the plant blowdown. Now what are the key conceptual and front-end design steps relevant to our process safeguarding systems that are applied in industries? So in general, there is process flow diagram and utility flow diagram which is developed. Then we also develop the process safeguarding philosophy. So what is the philosophy of protection for the plant in a major overall uh, context that we try to determine. Then perform hazard identification, prepare piping and instrumentation diagram. Then we perform a design review under which we study the design integrity of the system. Then we prepare the safeguarding memorandum under which we will enlist all the major safeguards that are available within the plant equipment wise. Then we prepare cause and effect matrices which will give you all the major IPF functions on what causes they are operating. Then we will execute HAZOP study. This will basically identify all the hazards that may cause due to any equipment operating outside its operating envelope. So all the keywords are applied and the major safeguards are then identified or are then required to be installed on the equipment as the outcome of the HAZOP study. Then update the design documents according to the studies. Prepare IPF narrative. So whatever the major IPF functions we have identified or we have designed as a part of the system, those are then applied for IPF classification review so that the seal classification of those IPF functions are determined, and then update the design documents accordingly. So let's say you found that your IPF seal classification for a separator inlet valve is coming to seal 3, whereas you have provided only you have not provided sufficient seal integrity valve, then you may need a multiple valve with a multiple number of identification element or the sensing element, and that will be guided by your control and automation representative. Then prepare functional logic diagrams. Now, what are the major international standards in the in the guidance of safeguarding philosophy? So, recommended practice for analysis and design installation and testing of basic surface safety system for offshore production platforms is done by API RP14C. Pressure relieving and depressuring system is majorly guided by API standard of 521 and ISO 23251, and venting and atmospheric and low pressure storage tanks is guided by API 2000. Thank you. Thank you very much.